Chapter 2 is titled Signals in the Time and Frequency Domain and describes mainly the Fourier Principle. We start with periodic signals because they are quite simple to discuss. Here you see 5 important forms of periodic signals. From the top to the bottom: sinus, triangle, rectangle, sawtooth, and extremely short impulses. From a theoretical point of view, periodic signals are of infinite duration. That is, they extend far beyond the illustrated segment into the past. That means in this direction. And into the future. That means in that direction. It is very easy to determine the period length and frequency of the individual signals. For example, see the sawtooth. This signal repeats 1, 2, 3, 4, 5, 6, 7, 8 times per second. Therefore, its frequency is 8 Hz. And the periodic length is 1 divided by 8. That means 125 milliseconds. Signals can be defined as physical oscillations or waves which are carriers of information. But how is it possible to recognize the information carried by the signal? In this experiment, a generator module produces in the first instance 3 different signals, of which the lower 2 are subsequently manipulated. The information value of the above signals increases from the top to the bottom. The signal above is a sinus whose course can be predicted exactly. After some time, there is no new information. The middle signal is a modulated sinusoidal signal. The amplitude follows a certain sinusoidal pattern. Finally, the signal at the bottom has a rather random course. It is filtered noise. It can be least well predicted, but contains, for example, all the information about the special characteristics of the filter. This is the fact. The more we know what message will be conveyed by a source, the less the uncertainty and therefore the information value. In daily life, information seems associated more with knowledge than with the idea of uncertainty, but not in information theory. The Fourier Principle makes it possible to regard all signals as composed of the same unified components. Simple experiments with Daisy Lab or with a signal generator, function generator, an oscilloscope, a loudspeaker with a built-in amplifier, and most important, your sense of hearing, lead to the insight which the French mathematician, natural scientist, and advisor to Napoleon discovered mathematically almost 200 years ago. Please see and listen to the next experiment, the Fourier Synthesis of a sawtooth. There is a single form of AC voltage which only has one audible tone, the sinusoidal signal. In these experiments, it is only a question of time before a certain suspicion arises. Thus, in the Sawtooth of 250 Hz, there is an audible sinus of 250 Hz, 500 Hz, 750 Hz, etc. This means that if we did not see the audible periodic sawtooth signal, our ear would make us think that we were simultaneously hearing sinusoidal signals of 250 Hz, 500 Hz, 750 Hz, etc. Please note that the picture on the right hand seems to show us the sinusoidal signals you can hear, their frequency and their strength, amplitude. The preliminary conclusions are: there is only one single oscillation which contains only one tone, the periodic sinusoidal signal. All the other periodic signals or oscillations, for instance tones and vowels, contain several tones. Our ear tells us one tone is one sinusoidal signal. This means several tones are several sinusoidal signals. All periodic signals, oscillations, apart from the sinus, contain several tones. The consequence is the extremely important Fourier Principle. All signals can be understood as consisting of nothing but sinusoidal signals of differing frequency and amplitude. The next logical conclusion is: if it is known how a given system reacts to sinusoidal signals of different frequencies, it is also clear how it reacts to all other signals, because all other signals are made up of nothing but sinusoidal oscillations. Suddenly, the entire field of communications engineering seems easier to understand, because it is sufficient to look closely at the sinusoidal signals of different frequencies. This is a second illustration of the Fourier synthesis. Using the example of a periodic sawtooth signal, it is shown that sawtooth-like signals arise by adding appropriate sinusoidal signals. Here are the first 6 of the theoretically infinite number of sinusoidal signals which are required to obtain a perfect linear sawtooth signal. The following can be clearly seen. In some places, 4 are visible here. All the sinusoidal functions have the value 0. At those points, the sawtooth or the sum has the value 0. Near the jump 0 position, all the sinusoidal signals on the left and on the right point in the same direction. The sum must therefore be greatest here. By contrast, all the sinusoidal signals almost completely eliminate each other near the flank 0 position, so that the sum is very small. This is very important. All periodic signals contain as sinusoidal components all the integer multiples of the base frequency as only these fit into the time frame of the period length t. The periodic sawtooth has 2 Hz. Therefore, the basic sinusoidal component has also the frequency 2 Hz. The next has 4 Hz, 6 Hz, etc. These are the multiples of the basic frequency. In the case of periodic signals, all the sinusoidal signals contained in them must be repeated after the period length t in the same manner. The next Fourier synthesis shows the basic rule: the more, the better. Here the first 32 sinusoidal signals have been added, from which a sawtooth signal is composed. Here the first 64, and here the first 128 have been added. At the jump position of the sawtooth, the deviation between the sum and the sawtooth is greatest. The cumulative function can never change faster than the sinusoidal signal with the greatest frequency. It is practically visible as ripple content. As the sawtooth at the jump position can theoretically change infinitely rapidly, the deviation can only have disappeared when the cumulative function also contains an infinitely rapidly changing sinusoidal signal. That means frequency versus infinity. If that doesn't exist, a perfect sawtooth signal cannot exist either. In nature, every change takes time. The more sinusoidal signals contained in the spectrum are added, the smaller is the deviation between the cumulative curve and the sawtooth. For the first time, you see now the picture-edit Fourier transformation. The illustration shows in a very graphic way the so-called Fourier transformation. The time and frequency domain are 2 different perspectives of the signal. A playing field for the essential sinusoidal signals, of which the periodic sawtooth signal presented here is composed, serves as the pictorial transformation between the 2 areas. The time domain results from the addition of all the sinus components, the harmonics. The frequency domain contains the data of the sinusoidal signals, amplitude and phases, plotted via the frequency f. The frequency spectrum includes the amplitude spectrum, shown on the right, and the phase spectrum, shown on the left. Both can be seen directly in the field of sinusoidal oscillations. The amplitudes of the sinusoidal components you see here. The reference of phase shifting can be seen at the left hand of the time axis. Therefore, the phase shifting changes here between 0 and pi. In addition, the cumulative curve of the first 8 sinusoidal signals presented here is also entered. There is now a calculating procedure, an algorithm, to calculate the frequency-based way of presentation, the spectrum, from the time domain of the signal and vice versa. This method is called the Fourier Transformation. It is one of the most important signal processes in physics and technology. The Fourier Transformation, ft, is the method of calculating the frequency spectrum of the signal from the progression in time. The inverse Fourier transformation, IFT, is the method of calculating the progression of a signal in time from the spectrum. Periodic signals have a line spectrum because the spectrum contains only the integer multiples of the base frequency. As a result of the Fourier principle, all oscillations or signals are seen from two perspectives. That means the time domain and the frequency domain. In the time domain, information is given on the values of a signal at any given time within a certain period of time. That means the time progression of the values at any given moment. In the frequency domain, the signal is described by the sinusoidal signals of which it is composed. Pulse forms without rapid transitions are very important for signal transmission. Within the periodic Gauss sequence of pulses, each pulse begins and ends gently. For this reason, the spectrum cannot contain any high frequencies. This characteristic makes Gauss pulses so interesting for many modern applications. We will come across this pulse form frequently. Here you see periodic square wave signals with different pulse duty factors. This illustration shows how the information from the time domain can be found in the frequency domain. The period length t is to be found in the distance 1 over t between the lines of the frequency spectrum. As in this illustration, t equals 1 second, resulting in a line distance of 1 Hertz. The pulse duration tau is 1/4 in the upper figure and 1/5 of the period length t in the lower figure. It is striking that every fourth harmonic is missing in the upper figure, and that every fifth harmonic is missing in the lower figure. The zero position is in each case at the point 1 over tau. Now it is also possible to determine the period length t and the pulse duration tau in the frequency domain. Now we take steps in the direction of a delta impulse. The pulse duty factor at the left becomes smaller and smaller. The zero position moves towards the right with higher frequencies if the impulses become narrower. In case of a needle impulse or delta impulse, the width of the impulse tends towards zero. Thus, the first zero position of the spectrum tends toward infinity. Hence, the delta impulse has an infinitely wide frequency spectrum. In addition, all the amplitudes are the same. Now we show the transfer from the periodic signal with a line spectrum to the non-periodic signal with a continuous spectrum. On the left, in the time domain, you see sequences of periodic rectangular pulses. The pulse frequency is nearly halved in each case, but the pulse width remains constant. Accordingly, the distance between the spectral lines becomes smaller and smaller. T equals 1 over f, but the position of the zero positions does not change as a result of the constant pulse duration. Finally, in the lower sequence, a one-time rectangular pulse can be shown. Theoretically, it has a period length infinity. The spectral lines lie infinitely close to each other. The spectrum is continuous and is drawn as a continuous function. The result is periodic oscillations or signals have a discrete line spectrum, whereas non-periodic oscillations or signals have a continuous spectrum.